all panelists. Today's speaker is Professor J.M. Cardot. Professor Cardot is the head of the Department of Biopharmaceutics and Pharmaceutical Technology at the Auvergne University in France. Prior to coming to Auvergne University, he worked in the pharmaceutical industry for 15 years. Professor Cardot earned degrees in pharmacy, a master's in biopharmaceutical statistical sciences and pharmacokinetics, and a doctorate in pharmaceutical sciences from the Auvergne University. His research interests include biopharmaceutical development of drugs, in vitro dissolution, in vivo bioequivalence, and in vitro in vivo correlation. J.M., welcome to today's event. I'll now turn it over to him to begin the presentation.
Thank you, Suzanne. Hello, everyone. So today we are going to discuss about IVIVC and time scaling. And among all those problems, we are going to see the, I have a problem to try to, We are going to see, first of all, what is IVIVC, what is a time scaling, when we can use a time scaling, what is a linear or nonlinear time scaling, and what is the problems and outcome with time scaling. I am going to use some data which were published previously in 2011, and you can find it in Pharmaceutics, and it's an open journal. That means all the data are open. So the first thing that we have to keep in mind when we discuss about IVIVC is that in vitro in vivo correlation is a link between in vitro data and in vivo performance. And very often the in vivo performance is going to be the pharmacokinetic data set. We are going to use IVIVC to weigh with in vitro data in vivo bioavailability or bioequivalence. So very often IVIVC are going to be used with the in vitro data as a surrogate of the in vivo. What is the aim? The aim is to reduce the in vivo bioavailability studies. That means to use it in vitro as a surrogate of in vivo bioequivalence. And we are going, in this case, if we have something which is quite correct with the IVIVC, to reduce the number of studies. We have three levels of IVIVC, which is the level A, B, and C. On the left side of the screen, you have the level A, which is going to try to link together the percent absorbed in vivo with the percent dissolved in vitro. We have to keep in mind that the percent absorbed in vivo in this case is going to reflect the slowest between the in vitro release of the drug, the in vivo solubilization of the drug, and the in vivo permeation. If we want to make an IVIVC, we have to suppose that what you are going to observe as the percent absorbed is going to reflect the in vivo release and dissolution of the drug. So we can try to link it with the percent dissolved in vitro. That is the level A, which is the more powerful level. Level B and C are going to try to connect any type of pharmacokinetic parameters with any type of in vitro parameters. For level B, it's going to be the mean dissolution time versus, for example, the mean residence time in vivo. That means we are going to have something which is going to be based on statistical moment. For level C, which is the less informative, is going to be any PK parameters versus any in vitro dissolution parameters. When we start to discuss about time scaling, we are going to have something which is going to be linked with a level A correlation. When we have a plasma concentration curve, we are going to have different shapes. For example, on the right side of this slide, you have the green one, which is the reference immediate release, and you have a free slow release formulation. The purple one, which is the B, the A, which is going to be the yellow one, and the C, which is the orange one. All what you see now here on both one on the slow release exhibit a longer action of the drug in the body, a sustained one, and a reduced Cmax, because the release in the body is less important. Can we be sure that what we are going to observe now is linked with the formulation? Yes, we can, if we have a same active ingredient in quality source and, if possible, batches between all the test formulations. In this case, the difference is going to be linked only with the formulation. Vice versa, if you keep constant the formulation but you change the quality or the grade of the API, all the difference that you are going to see in vivo are going to be related with the API. What is an IVIVC level A in theory? We start by the left part of this slide. You give a tablet to the subject. You are going to have on the top part of this slide in vivo data, time concentrations. On the bottom one, you are going to have the in vitro dissolution. What are you going to do from the in vivo data? You are going to try to extract, and that is in the middle of the slide top, the absorption curve. And I remind you that this absorption curve is going to reflect the in vivo release, the in vivo dissolution, and the in vivo permeation of the drug. And we assume that we are going to see the slowest one, which is going to be the something like in vitro data. You are going to try to link the in vivo absorption, which is going to reflect the release in dissolution if it's a slow release formulation, versus the in vitro dissolution to make a relationship. What are we going to do when you have a new formulation, which is the yellow one in the bottom right part of this slide? You are going to have the in vitro data. Using your correlation, you can predict the absorption and then the plasma concentrations. That seems to be very easy. I make a next slide, which is very complicated, and we are not going to go in detail for the next slide, but in reality, IVIVC are a little bit more complicated. You have a lot of steps, and we are going to see some of them today, which is the time scaling one. We can use IVIVC mainly for the slow release formulation. That can be peros, PO, or oral slow release formulation. That can be parenteral formulation like suspension, implant, or depot. That can be intrauterine devices, IUD, or vaginal rings. That can be patches or transdermal therapeutic system, TTS. We can also use it, for example, when you have inhaled products. The time scaling is going to be something that we are going to use when we have sometimes oral formulations, but very often when you have very, very slow release formulations. For example, when you have an implant which is lasting for 3 years in the body, you are never going to do a dissolution over 3 years. That means the dissolution is going to be faster than the in vivo absorption or release. So in this case, you are going to use something which is going to be a time scaling to fit what you are going to observe in vivo and in vitro. We are going to go through examples. When you have an in vitro which is faster than in vivo, and you have a level A, it's exactly what you observe in this slide. This is for the peros formulation corresponding to the curves that I presented you just before. You have in this case formulation A, B, and C, and on the right up side of this slide, you have the absorption. That means the fraction input versus time. You can see that you have for the formulation A something which is going to last for around 10 to 12 hours for the absorption. The B, it's around 16 hours, and the C, it's almost 20 to 24 hours. On the bottom right part of this slide, you have the in vitro dissolution. You can see that the in vitro dissolution for the formulation A, B, and C are faster than the in vivo. We have exactly the same time scale between the two here. So that means if I want to make an IVIVC, I will finish to dissolve, but I continue to absorb. In addition, when I start to study the absorption curve, I can see that I have something which seems to be more biphasic. That means a phase up to 4 hours and something which is lower after 4 hours. But when I have a look on the dissolution, I don't have these two phases. That do mean that I don't have exactly the same processes between in vivo and in vitro. Second problem that I will have is how can I fit my in vitro data? And we are going to see that later on. If I make, based on those data, a classical IVIVC, I will have something like this. How can I do a classical IVIVC? I am going to correlate the same time in vitro and in vivo. That means I have, for example, dissolution and absorption at half an hour, 1 hour, 2 hours, and so on. I am going to make one point at the same time in vitro and in vivo. This is what I can observe in this case on the left side of this slide. I have my classical IVIVC with in x-axis the dissolution and in the y-axis, the absorption in percent. What I observe? I observe something which is quite classical. I have, for example, for the first time, almost 0 as percent absorbed, but something which starts to dissolve. Why? Because I have a lag time in vivo. Then I start to absorb and dissolve at the same times, and at the end you can see that when I have finished to dissolve at 100%, I have a curve which is going up. This curve going up, which is in the circle here, corresponds to a problem of time scaling linked with a faster in vitro release compared to the in vivo. I have finished to dissolve, but I continue to absorb. Clearly, in this case, the dissolution is more rapid than the absorption. How can I solve it? I can solve it with a lot of possibilities. The first one is to develop a new dissolution test. Something, for example, which is going to be slower in dissolution. That is still possible when you have an absorption over 24 hours, but when you have an implant which is going to release over 3 years, you can it will be very complicated to develop a dissolution over 3 years. For example, you will not be able to release the batches before 3 years. So very often we are going in this case to have a dissolution which is going to be faster than the in vivo release. And we cannot solve this problem that we have seen just before. Second possibility, we can make a non-linear IVIVC, but we have a lot of drawbacks in that. Non-linear equations means that we are going, in this case, to have something which is going not to reflect exactly what we observe at the end. The third possibility, which is more simple and obvious in a two-stage approach, is to make a time scaling. We are going to try to find which is the time in vitro corresponding to what we observe in vivo. We are going in this case, and we are going to see that in the next curves and slides, to try to make a link between the in vitro and in vivo. When you have the right time scaling for all the formulation, at the end the in vitro must be almost equal to the in vivo. That means you must have something which is very close to a one-to-one relationship. If you have something like this, that do mean that the right time scaling was applied. So how are we going to do a time scaling? We are not going to work anymore on the same time between in vitro and in vivo, but on the same quantities of percent dissolved and absorbed. That means on the graphic on the top of these slides, we are not going to work anymore with the vertical lines, but the horizontal lines. I am going to select, for example, on the left part of this slide, the quantity which are going to be absorbed, or the percentage which are going to be absorbed at a certain time. Then I'm going to make the horizontal line and to try to find at which time I have exactly the same quantity or percentage which are dissolved. For each percentage absorbed in vivo, I'm going to try to calculate what is the time to have exactly the same thing in vitro for each of the curves. We are going to see that in detail with another example. What can I have as a link? I can have, like in the bottom right part of this slide, something which is a linear line. I can have on the bottom left something which is biphasic or non-linear. What is the meaning of that? If I have a linear relationship for my time scaling between the time in vivo and in vitro, that do mean that I have the same type of release mechanisms in vitro and in vivo, but not at the same rate. One is faster than the other. If I have something which is biphasic, which is the yellow bottom line here, that do mean that I have two phases, in vitro versus in vivo, or in vivo versus in vitro. That means I have the mechanisms of release which is non-constant either in vitro compared to in vivo, or in vivo compared to in vitro. And we have to try to understand why. That could be due, for example, to the fact that we keep constant something in vitro, but we have a mechanisms of release in vivo, which is going to correspond to two types of release or two sections or segments of release. For example, if we take what we have observed here, we have something which is faster in vivo than in vitro, which is the upper curve on the right part here. You have a first order in vitro, you have a first order in vivo, and in this case you have the same release mechanisms between in vitro and in vivo, but not at the same rate, and we are going to have a linear line. What was reflecting my yellow curve? That was reflecting something which is a constant rate of release, for example, in vitro, but a non-constant rate in vivo. If we have some formulation for porous formulation, that means oral formulation like erodible matrices, the release is going to depend on the hydrodynamic around the matrix. In the small intestine, I am going to have something which is going to be a faster release in vivo than in vitro. And then, when I go to the large intestine, I am going to have something which is going to slow down in vivo, but maybe not in vitro if you have kept constant the parameters of your dissolution. In this case, I'm going to have a non-linear time scaling linked with the position of my tablet in my gut compared to my vessel with exactly the same in vitro dissolution techniques. So, when I have, to summarize what I have said up to now, when I have exactly the same phenomenon in vitro and in vivo but not at the same rate, for example, first order release in vivo and first order release in vitro, I am going to have a straight line. And you can see here on the top part of this curve that the time in vivo is from 0 to 24 hours, but the time in vitro is for 0 to 12 hours, for example, but my straight line is here. That means I have a first order, for example, in vivo and in vitro. That means the same release mechanisms between the two. Vice versa, when I have something which is biphasic in vivo but monophasic in vitro because I have not modified my dissolution techniques, I'm going to have a time scaling which is going to show two slopes. The first one corresponding to the first part of my release in vivo, knowing that I have kept constant my dissolution in vitro, and the second one which is going to correspond to my second set of release in vivo and not in vitro. Why does I have something like this? I have something like this, for example, because I have an erodible matrix. And depending at the beginning from 0 to 4 hours, if I am in the small intestine, I am going to have a faster erosion compared to the colon, where my erosion is going to be slower. But if I have kept constant, for example, my in vitro dissolution technology to 50 RPM all along my dissolution, I will not see those two phases in vitro, even if I have them in vivo. This is the formulation of the slide 5, and that which is a biphasic one. This is made by scintigraphy, and you can see that this formulation, when at 0 hours, is in the stomach, 1.5 hours in the small intestine, at 3.5 hours just at the beginning or the end of the small intestine or beginning of the colon, at 6 hours on the top of the ascendant colon, at 10 hours at the middle of the transverse columns, and 24 hours almost out. This matrix is an erodible matrix. That means its release is going to depend on the hydrodynamic. The hydrodynamic, that is the movement and the quantity of water that I have in presence of my drug, is going to be larger in the small intestine for the movement compared to the colon. So that means I can expect for this formulation to have a faster release from 0 to 3.5 or almost 4 hours, and then a decreased release after that because I'm in the colon. If I have set my in vitro dissolution always at 50 RPM, I will not see those differences. That will explain why I have a biphasic time scaling comparing my in vitro to my in vivo. That is due to the position of my tablet in my body. So, to start again with exactly the same data and to make step by step what I am going to do to make this time scaling. You have on the left part of this slide in the bottom my in vivo release, that means my in vivo absorption, which is going to represent my in vivo release, my in vivo dissolution, and my in vivo permeation. It is a class 1 drug, so that means no problem of permeation. What I see here is a slow release formulation is going to correspond to my in vivo release and dissolution, something that I can mimic in vitro. you have seen that I have a faster dissolution, in vivo release or dissolution up to 4 hours, which could be the time of the colonic entry. That means the change of the hydrodynamic. If you take the formulation C, you can see that there's something which is fast to almost 4 hours, and then a second slope which is really slower. That could be linked with the fact that from 0 to 4 hours I am in the small intestine, huge erosion, faster release, and from 4 hours onward, a slowest hydrodynamic condition, so that means the slowest release in vivo. On the right part of this slide, I have my in vitro dissolution test. It's 50 rpm, constant from 0 to 24 hours. So that means I will not see in vitro both modification of hydrodynamic conditions and something which is almost linear. So I will expect in this case to have a non-linear time scaling. So how can I use Phoenix to do it? In Phoenix, outside of the IVIVC toolkit, I have a Levy modules, I have deconvolution, convolution modules, classical, but I need URL. I have linear regression with 3 types, linear, what I am going to use for the IVIVC, quadratic and cubic. Dissolution, I have 4 functions only, which is Weibull, Hill, double Weibull, and McCoy-Banachar. I have data wizard to perform custom calculations. I have all the data, merge, joins, append of my files, and so on. That means I have everything that I can use to make any IVIVC and time scalings. The advantages of Phoenix is that I can trace all the operation that I'm going to do. So the first thing that I have to do is to feed the dissolution data. To feed the dissolution data, I can use the dissolution tool. In this dissolution tool, I have 4 models, which are Hill, Weibull, double Weibull, and McCoy-Banachar equations. So I'm going to try to fit my slow release formulation. One case that I can have here is at the end. For example, when I try to fit the formulation C, you can see that the F infinity is not going to be 100% dissolved, but try to be larger. Why? Because it's better to fit all my points. I have something here which is 269% dissolved, which is not possible. What I can do to avoid this type of mistake, because anyway, even if you make a model which is going to be used to interpolate the missing points, this model must reflect the reality. So I can try to find a better function. I can try to limit the dissolution data, for example, discarding some points. I can try also to fix the F infinity at the maximum to 100. Is that 100 possible? Not really. Why? Because somehow, when you have a formulation, you have a content of your drug inside. And very often, this content of drug can be versus the label 105 or up to 110% or even more. So that means if you want to fix the F infinity, you must fix it to 105, which is the maximum limit of content, or 110%, depending on what is in your certificate of analysis. Fitting dissolution data is not something which is so easy. If we take the formulation B, which was a medium formulation, we are going to try a lot of possibilities. The first one is, for example, here, to use the classical one. You can see that my fitting curve with a Weibull function is not perfect. It's not perfect. Why? Because Weibull function is going to simulate either something which is parabolic, something which is going to be exponential when B is close to 1, or something which is going to be sigmoidal when the B is larger than 1. And in this case, you can see on the left part of this slide, my dissolution curve are not really either exponential or sigmoids. I can say, okay, I remove my plateau. If I remove my plateau, I can try to fit it still with a Weibull function, fixing the F infinity close to 100. But you can see that in this case is the higher point which are not well established. If I remove these points but I let the F infinity going to what I want, I have the third curve starting from the left side. you can see that in this case, the F infinity is going to go to 1,266%. Why? Because I have something with, I remove the plateau, which seems to increase all the time and without any data to end it. Other possibility is to fit it with a quadratic equation. I can do it also, and I have something which is not so bad. So what can I have in this case? Either to fix the F infinity to a number which can be 100 or 105%, or to use a quadratic equation. The quadratic equation is not in the dissolution tool of Phoenix, but in the linear relationship tool of Phoenix. So the second thing that I have to perform is the deconvolution. To make the deconvolution, I need to have a UIR. First of all, I can have it here. In this case, I have, you have seen, an immediate release formulation. I can use something with, in this case, a fit of my immediate release formulation with a first order input, which is an absorption rate constant Ka, or I can also try to fit it with a zero order like an infusion, and in this case I will use the infusion tool, knowing that the Tmax is going to be corresponding to the end of your zero order input. That means, into quote, the end of your infusion, even if you are in PO. You are going to calculate your macro coefficient and macro exponent, and you are going to adjust them to a dose of 1, independently of your initial dose. Why? Because this unit impulse response, that means it's for one unity, for 1. Then you are going to perform your deconvolution, and the result of the deconvolution is exactly what you observe here on the right part of this curve. Knowing when you are going to make the deconvolution, you have to use the observed time point as input to have exactly the point corresponding to your plasma concentrations. When you don't have any UIR, you can use Wagner-Nelson equation if your drug behaves as a one-compartment model. So now I have my dissolution, I have fit my dissolution. I have my absorption, but you have seen that I have not fit my absorption. I use what which was given by my deconvolution tool, and I am not going to try to fit it. Now I am going to try to make a time scaling. But making the time scaling is not guessing what is the right time in vitro corresponding to the in vivo. I am going to use my equation that I use to model my dissolution. For example, I can use a Weibull model. You have it on the second line here. Weibull dissolution is corresponding to F infinity times 1 minus exponential of minus T divided by mdt power of B and so on. Or I can use a quadratic one. So that do mean that in this case I have my dissolution, which is going to be a function of some parameters. Time, of course, but also if I am quadratic, A2, A1, A0. If I have a Weibull function, my dissolution is going to be a function of the time, but also the F infinity, mdt, and B. Now I want to calculate my time scaling. What I am going to do? I want to calculate something which is the time at which I am going to observe in dissolution exactly what I had observed in my absorption curve. So I am going to use an inverse function of my dissolution function. Only to give you that as an example, I gave here the inverse of the Weibull function. When you have it, what you are going to do? In the Weibull equation, you are going to replace the dissolution at time t, but by the absorption at the time t. Based on that, as you know the F infinity, the mdt, and the B, you are going to extract from this equation the time at which you observe in vitro a certain percent absorbed in vivo. So that means the time scaling for each points that you have in vivo is going to be equal for a Weibull equation to minus log, natural logarithm in this case, because you have an exponential, of minus absorption divided by F infinity plus 1, that as a power of 1 minus B, multiplied by mdt. So based on all the points that you observe in vivo, you are going to calculate each time at which you are going to have exactly the same quantity dissolved in vitro. You see here that I start from what I observe in vivo. Why? Because you cannot modify it. It's what you have observed. It's more easy if you need to redo a dissolution with a new sampling time than to redo a new in vivo study. So what I am going to have here, I am going to have calculated all the time in vitro, which is going to give me the same percent dissolved in vitro to what I had observed as a percent absorbed in vivo. So I have time in vivo which are fixed by my sampling schedule, and I am going to put in relation, in this case, all the time in vitro which is going to revert exactly the same percentage dissolved. So I have used an inverse function, and I gave you here the inverse of the Weibull function. How can you do it? You are not going to do it in Excel. You can if you want. But as you have entered all the data in Phoenix, you are going to use the data wizard to do it. You are going to implement in Phoenix, in the data wizard, a custom function, which is going to be your time scaling function. And you enter here the function which you can see on the upper panel here, minus log of minus abs divided by f infinity plus 1 and so on. Abs is given by your deconvolution. F infinity, b and ndt for the Weibull function, for example, are going to be given by the dissolution toolpack that you have in Phoenix. You can use, of course, if you prefer, the mean or the median of the absorption for the calculation of the time scaling. So, for example, on the lower part here of this slide and left one, you have the dissolution after scaling versus the absorption after scaling, and you can see that they have almost a one-to-one relationship. On the right part here of this bottom part of the curve, you have my time scaling. And this time scaling is something which is quite easy. You put on the x-axis the time in vivo and the y-axis the time in vitro. You are going to tell me, but why do you use in this case the time vivo on the x-axis and the time vitro on the y-axis? For a very simple reason. The time vivo is something that you observed, but you do not touch it. It's going to be your input in your function. It's something which is going to be fixed. And based on this x, which is going to be fixed, you are going to calculate the time in vitro, that you are going to put on the y-axis. You can see that after the time scaling calculation for my three formulations, A, B, and C, I have something which is almost constant up to 12 hours, and then something which is a little bit different later on. I have something which is almost constant up to 12 hours in vivo. Formulation A then returns something which is a straight line. Why? Because they have finished to absorb and finished to dissolve. So I have exactly the same value at the end. I have something also with a breaking line around 4 hours in vivo. That is the time at which I enter my formulation in the colon. So I modify the release mechanisms and rate in vivo between the small intestine and the colon, but as I have kept constant all my parameters of dissolution, I will not see it in my dissolution. That means my time scaling is non-linear in this case, a first time scaling up to 4 hours, and then a second time scaling from 4 hours onward. I remind you that, and I told it to you just before, after my time scaling, I have an IVIVC, which is almost a one-to-one relationship. You can see that my in vivo percent absorbed corresponds to 1.03 times my dissolution after scaling plus 1.3%. That means after my time scaling, I have a relationship for my IVIVC, which is in vivo absorption corresponds to in vitro absorption plus 3%. Now you have your time scaling. You put in vivo in X for the time scaling and in vitro on the Y. I have three curves, A, B, and C. What I am going to use? I'm going to use either the mean curve of my time scaling or the median curve, but I am going to use the same time scaling for my three formulations, A, B, and C, and I am not going to modify the time scaling depending on the formulation. That must be something which is common for all the formulations because the time scaling is dependent of your technology and not of the release rate of your formulation with your technologies. So I have a biphasic, nonlinear time scaling in this case. I know why. It's due to physiology, time at which I enter in the column. Time scaling and IVIVC. When I have a good time scaling, I will have an IVIVC which is going to be almost a one-to-one relationship after my time scaling. The time scaling is used in place of the IVIVC to correct the in vitro to the in vivo data. That means my time scaling is going to give me my relationship between in vitro and in vivo data. My time scaling will give me my sampling time in vitro, which is going to reflect my in vivo. That means I can adjust my sampling in vitro on my time scaling. And I can fix also my dissolution time points for my QC based on my time scaling to reflect, for example, 20, 50, and 80% absorbed. So, IVIVC without and with time scaling. On the left part of this slide, I have my IVIVC relationship without my time scaling. You can see, as I told you at the beginning, when I have 100% dissolved, I continue to absorb because my absorption rate, which is reflecting my in vivo release and in vivo dissolution for this class 1 drug, is slower than my in vitro dissolution. On the right part of this slide, I have my time scaling. On the upper part, I have the common time scaling for my three formulations, and on the bottom, I have my IVIVC after the time scaling. You can see that all the three formulations now are all together. That means my time scaling, which is a median curve here on the top of this slide, will allow me to have a common time scaling for the three formulations A, B, and C. If I try to make my predictability, that means to predict my in vivo time concentration based on my IVIVC and my dissolution, without the time scaling, you can see that I fail. This is on the left part of the slide. I underestimate the Cmaxes, and I have a shift of my Tmax. Why? Because my dissolution is faster than my absorption. With the common time scaling, which is on the right part of this slide for the three formulations A, B, and C, you can see that I can predict accurately the Tmax, the Cmax, and the AUC of the three formulations. So with my time scaling, which is common for the three formulations, I have a successful IVIVC. Which are the regulatory requirements? That means, can I use a time scaling? Can I use a nonlinear time scaling? What we have in the guideline is that the time scaling is allowed if the time scaling is the same for all the formulations. That is in the FDA, not for guidance, but also in the AMEA guideline. So what is important to keep in mind is that the time scaling must be common for all the formulations and not formulation dependent. That means the time scaling is something which is common for your technology, but independent of the release rate linked with your technology. Phoenix. Phoenix can help you to trace all the calculations. That means when you have a custom function, when you make your deconvolution, when you make your dissolution modeling, everything is traced in the log and also as a result. When you change something, the results are going to be changed if you rerun Phoenix. If you don't rerun Phoenix, it's going to be in red. That means you see that you have changed something. You enter only time concentration and time dissolution once, and all the rest is going to be monitored by Phoenix and also traceable by Phoenix. That means you secure all the processes. You have quite a lot of flexibility. You have a lot of flexibility because you have more than one dissolution model. You can even use your own custom models, but you must program and use the right equation. That means sometimes you must be able to use the constant function of the data wizard to put your own equations, for example, the inverse of variable. So time scaling, it's not something which is so easy because you have to think a little bit about it before. For example, I show you that you may have problem to have a fitting of your dissolution which has a meaning. For example, if you let the software make the fit of your dissolution curve and you return a F infinity corresponding to 1000% dissolve, is meaningless in terms of dissolution. So that means your equation maybe is going to reflect accurately your points, but you cannot use it to simulate your in vitro dissolution to a time point which is greater than the last one that you have used. You need to understand the needs and also the purpose of a time scaling. That means you make a time scaling when your in vitro dissolution is faster than your in vivo absorption, which is going to reflect your in vivo release. You have not to use it sometime, but you have to use it other time. A nonlinear time scaling is possible. The time scaling must be the same for all the formulation. It depends on the release technology and not depending of something else. Sometimes you need to redevelop a dissolution test. But also, you have to keep in mind that after a time scaling, your IVIVC must be close to a one-to-one relationship. Because if you make a time scaling, that means you modify the link between your in vitro and in vivo. And then you redo later on a new IVIVC with a second equations, you are not sure anymore about the robustness of your IVIVC. So I am open to any questions, and I think that I am going to give the hand back to Suzanne. Is that correct?
Yep. Thank you so much, JM. As JM has mentioned, we'd love for our audience members to enter their questions for Professor Cardot into the Q&A section. First question from our audience. Someone would like you to suggest optimal dissolution media and the duration of dissolution time.
So, yes and no. I can tell you, first of all, you have to try always to make use dissolution media which are described in pharmacopoeia. The same thing for the tools, that means dissolution systems like USP 1, 2, 3, 4, 5, 6, 7, and so on. But you are quite open to use something even which is not compendial if it's going to reflect what you observe in vivo. Not compendial, for example, I can give you a very simple thing. If you use FACIF and FACIF, that is not compendial. But if that is going to reflect what you observe in vivo, it's perfect. Maximum duration of dissolution time, I would tell you something which is not a good answer. The dissolution time, you have to take care about two things. The first one, which is how long I can monitor my dissolution accurately. For example, if you have a dissolution which is going to last more than 48, 72 hours, are you sure that you are not going to have a modification of the volume due to evaporation? For example, only something which is as simple as that. Is your drug still stable in your dissolution media? So I would suggest that the dissolution is maximum 24 to 48, maybe 72 hours, not more, except maybe if you are in a closed system like USP4. And as a dissolution media, I would start always with aqueous media, described in pharmacopoeia. You can add sometimes of surfactants, and if nothing is working, which is simple, you can try to make something which is quite more complicated, but you have to show to the authorities that the simple tools are not working. And
I would like to know, go ahead.
No, it was the next question. Why don't you use a Levy plot to determine the time scaling? What I have used is a Levy plot, but I don't call it Levy plot. And the Levy plot of the Phoenix toolkit has only one drawback. It's not very easy to fit nonlinear time scaling with a Levy plot, which is, for the time being, within the IVIVC toolkit. I don't know if I have that answer or not to the question.
Someone would like to know, what are the limitations in the equations used for modeling dissolution?
I will tell you that the equation to fit the dissolution curve must not be over-parameterized. That means, for example, if you have 5 dissolution points and you use 6 parameters, you will have a perfect fix, which is meaningless. So that means the number of parameters that you are going to use to fit your dissolution curve must be in relation with the number of points that you have in your dissolution. And I will tell you that in the other way around. In a lot of guidelines, when you want to compare dissolution curves and you cannot use F2 test, and they tell you to use a MSD test, for example, with the parameters of the equations, they restrict the number of parameters to 3. Okay? So I will tell you 3, 4, maximum maybe.
Okay, it looks like we have one more question from our audience. Someone would like to know, what are, do I need to fit a nonlinear time scaling before using it?
Yes and no. It's a good question. If you have a linear time scaling, it's not very complicated, and that reflects that you have the same phenomena in vitro and vivo, but not at the same rate. When you have a nonlinear time scaling and you need, for example, for a new formulation to interpolate points, you may need to fit it. But the same thing here, you have to fit it with the number of points parameters which is going to be related with your number of points to avoid over-parameterizations. And one problem that you can have if you want to use a nonlinear fitting for your time scaling is that not to use something which is too flexible. For example, if you use polynomial equations, you may have problem in this case because you can fit almost all the type of curves when you increase the number of polynomials. So that means when you do it, you have really to try to fit it with something which seems to be quite accurate, I would say, to fit it. But you can do it, of course, and that is quite important if you need to interpolate new points.